Okay, so we're going to jump to the next two speakers. Inés Ariza is an architect and researcher from Buenos Aires. Through her current research work, Inés is developing an adaptive detailing workflow using WAAM, so wire arc additive manufacturing, as a joining technique for robotic assembly of spatial metal structures. Her diploma was received with honours from the University of Buenos Aires in 2011 and her Masters of Science in Design and Computation from MIT in 2016. Since October 2017, Inés is a Ph.D. researcher at the Chair of Architecture and Digital Fabrication, which is directed by Fabio Gramazio and Matthias Kohler at the ETH in Zurich. Inés, welcome. Over to you.
So I'm Inés Ariza. I'm a PhD researcher at Gramazio Research, the Chair of Architecture and Digital Fabrication at ETH Zurich. And I'm going to present today the work on my PhD that is called Adaptive Detailing with Wire and Arc Additive Manufacturing, WAAM. And some comments. I'm super excited about what I just seen. Thank you so much for the invitation. Very good start and also the questions. So very looking forward to your questions at the end. So the PhD presents a method for designing and fabricating connection details for non-standard structures using WAAM. So today I'm going to show a little bit why we're doing this and also how we are doing this. So a little bit of background. So these are digital fabricated projects, very state of the art of what's happening. We see basically a blow up on the scale of the things are being built with digital fabrication. The scale, but also the performance and basically really pushing the limits of the materials and what basically can be built. If we see under like how is this being built? So the technologies used for this, we see a lot of improvements and particularly creativity in the use of every single thing. So for example, just depositing materials in completely innovative geometries and varying geometries, or combining processes, multi-robotic processes or cooperative processes, also inventing new tools and using completely new materials that were not available at all in architecture before. And the possibility of, for example, mass customizing the position of the material. And also a very interesting line of research that is basically using non-standard materials that with feedback processes, we can basically scan them and bring them into the digital process. So so basically the background right now looks very staggering, amazing, impressive, the work that is being conducted, particularly at research institutions. And this contrasts a little bit with two other scenarios, which is one is the automation in the automotive industry. So for example, this is robotic welding, one of the first automated processes, which is extremely in high development right now, and it's fully controlled and very in contrast with what we see in the construction side, which is basically a complete manual process that has to be repeated each time, and it's different each time. So I think there is a gap between what I just showed before, which is this creativity in architecture and design, and the quality of automation, but also what is actually happening in construction on site. So to a certain extent, it is understandable that we cannot basically have the same situation. So architecture is actually unique and it cannot be repeated each time. So we are actually concerned with inventing something new each time, even if we want to optimize some processes, we're still pushing, and each time we build something, this is something unique because it has to accommodate to its particular requirements. So this is a structure bit at ETH Zurich, also at Gramazio Research, where two robots are used to assemble standard elements in a non-standard configuration, given a particular volume, like a defined volume and assembly sequence. In this case, the two robots are used to place the material, the bars in place, and then the joining is done by hand. Still a combination in a way of a very sophisticated setup with two robots hanging from the floor, from the ceiling, and a manual process in between. So here the manual process was very important because still, even if we can imagine that this is super high precision, in a way, actually there are a lot of uncertainties in the process. So the location of these end effectors, but also the deformation of the material itself. So the manual welding at the end was very useful. So one of the next steps and where the project starts is basically how to incorporate or where to see the opportunities of using robotic fabrication for solving this problem programmatically. So there are strategies and of course a lot of challenges, and I hope many opportunities to discuss of doing this with WAAM. So what is WAAM? So WAAM is an additive manufacturing technique that is basically welding technique. It's a welding process with a welding torch attached to a robot and to deposit material in space. And the particular quality here is that we don't need additional support. So WAAM actually, it's all over the place at the moment. So since 2012 have been growing exponentially, the research on this technology. This is how the map was looking in 2018. And since then, actually, the amount of things that have shown up is amazing. So there is basically a very fast growing field of research in additive manufacturing. So the technique was particularly interesting at the beginning for the aerospace industry, particularly because there is a high deposition rate, so we can deposit material fairly quickly compared to other additive manufacturing processes in metal. So the possibility of building large size basically was very interesting. And this project, the MX3D Bridge, was the first to really show or showcase to the world that we can actually build structural components with this technique. MX3D also explored other deposition strategies very early on. So this is, for example, discrete deposition, where also building the whole structure, but now with a discrete point-by-point welding. So what we're doing is slightly different, taking the discrete deposition strategy, but only printing the material that is in between parts that are already existing. So of course, here is a matter of time, saving time to not print the whole thing, but only print where we need customization. To illustrate this point a bit better, I'm going to compare to other connections for discrete structures. So take, for example, the standard connection that you can relate to regular structure domes, space frames, where every single connection or almost all of them are the same. So this relates to a standard production process where it's basically mass industrialized. Every single piece is the same. Even fabricated with digital fabrication, there's no variation in the pieces. So of course, very interesting, particularly cheap or reliable, that every single joint will look the same and it will work. But at the same time, it presupposes a lot of uniformity and restriction in the standardization of the overall shape. So lately we've seen other approach, which is, this is here very meaningful, the custom connection detail available thanks to additive manufacturing. So basically this is the mass customization of these nodes, where basically we can locally design each of these nodes according to a particular problem. So we can design these nodes based on geometric aspects or structural loads that within an assembly, of course, is changing. So we can see basically, quite diverse things also in metal in these three cases. This approach is quite interesting and also motivated a lot of research and a lot of projects on that direction. But it has this, of course, this challenge of the post-processing of the parts. So how to actually post-process the part after. So because the part is done in a separate process, then we have to actually prepare it to actually build with it. And of course, if we actually take this very extreme and we take parts, each of these joints are different, then we'll have a challenge basically on the construction side on how to assemble all this very heterogeneous puzzle. Of course, there is also the question of what type of environment we're building on. So for example, if the assembly is done on site and we don't have a high precision environment, it might be that these joints might not even fit. So basically it's a very predefined strategy. In that respect, there is a lot of studies at the moment in WAAM. So exploring this approach, building basically prefabricated components or prefabricated connectors that can then be assembled to be part of a larger assembly. We have examples, very high quality examples with continuous printing, most of them. And the latest is also an interesting reference that is print on top of an existing member as the one in the right down low. So in this respect, I continue more in this direction and propose an adaptive connection detail that is basically not fully baked before the construction starts, but basically the geometry is adaptive to the actual location of the members. So in this respect, we skip some post-processing, and we also make sure that the geometry fits to the actual location of the parts. So we'll see now a video. It's running. Just a comment if you're sensitive to light, because there is welding on it. So yeah, so we start basically mapping the reachable space at the robot and finding a place where to put a joint. Then localizing the members to identify the actual location of the bars. This can be done because we are using standard elements. In the case of other non-standard elements, could be done with other sensing strategies, as the project we just seen before. So basically we locate the bars and update the location on the digital model of these parts. Then we're ready for welding. So the first step is basically actually more defined scanning process that is basically finding the starting points of the part that we're going to build. So we can update basically the entry and the exit points of the joint that we design before starting. And then we can print really on top of this information. So then the printing process is basically point by point, so discrete. And here an important aspect is that we can use the time that we need for cooling time to actually move around between different points to optimize the process a little bit. So the uncertainty on the material needs a second measurement, so we cannot know exactly where the final layer height is. So we can scan again, basically the structure, and then print on top of that final layer. This is done with touch sensing, that is basically using the wire as a conductive to know, as a probe, to know exactly where is located, where is the structure is located. An aspect that is dedicated to in-place WAAM is that we're always printing in between other elements. So the big challenge is how to print to avoid collisions. We will see a bit more of that in a second. Now we have, at the very end, we scan again the final points. And then we finalize the join. To assemble. So we don't have more of the collision, but basically this is one of the most challenges. I have some slides at the end that to discuss that better. So yeah, so then basically that's the joint. Good. So we go back to here. So here is a pipeline of the things that are involved with a process like that. There are many aspects, and the important thing is that not all these things are necessary to actually build a connection like this. What I just show is a very simple connection that is basically two arms to support a piece. In this case, we only use basically localization and the reachability map to know where the robot can print to avoid collisions, path finding and path slicing, and then printing and touch sensing. But we can imagine that basically this can get more and more complex when we know more about the material behavior and the requirements, the functional requirements, like the structural requirements of the joint. So the idea of this pipeline is that it's flexible to add basically independent processes that can feed in more information as we know. In a way, more or less how we think about details, that we don't know everything when we start designing, but actually we are learning about the process as we design a connection. So yeah, so assume on part of the process on the design, we have basically the accessibility, reachability, which is the fabrication constraints to basically understand geometrically what is accessible, first for the torch, but then for the robot. So we do a reachability map to know exactly in which locations the robot can actually move and have many chances of actually reaching a possible configuration. And then we use this box or this kind of box as a design space for material distribution. So to know where the load paths are to actually distribute material in the best possible locations. With this, it's important to note that after that, we still need to keep in mind the fabrication constraints or the material constraints, in particular. So this is a result of a top-up, for example, where we can find paths that are printable, but still we need to, again, adjust this path to be able to print without collisions. So the concept basically goes back to this idea that instead of having a fully baked connection detail from the beginning, as in the planning phase, the connection detail is actually very open and updated during the build-up process, particularly based on two aspects. There is one, the actual location of the parts, but second, the material results that at this point we cannot fully simulate. So it's very useful to be able to still scan and adapt to what we actually get. So maybe to go to also the questions that Roland is asking, what can we build with this? and how does it change how we design? There is a lot to explore. And of course, the main thing now is actually getting the technique to actually run and work. But some things we tried is basically using this as small structures of linear elements or curved elements or more complex even network elements. In all of these, there is one aspect that remains, that is this basically spatial configuration, that we're always outside. So basically the node is being spatialized, I don't know, like outside of the normal point where the joint is. So that makes it more visible and expressive. So some open challenges on this, there are many, but some of the ones that are imminent is to ensure basically the repeatability of the process. So in particular, control the process parameters. One thing is controlling the process parameter for a standard, or let's say a known condition, and another is understanding basically what can be built in terms of geometries, in which directions of printing angles and curvatures we can print. So this is a big challenge because, of course, it's a lot of testing to understand and control the process. Related to that, in particularly to this technique, the aspect of the torch orientation. So basically, to avoid collisions, the torch cannot be aligned with the path most of the times. So this is actually one of the reasons why to actually spatialize the node and put it outside, the material outside as much as possible, so to actually be able to access it. But also can be that basically the torch orients in different configurations to avoid the collisions, and it still actually works. So this it's path printed with 45 degrees, and it's still it's a good result, let's say. Another challenge is related to the heat, and this is a big topic, and a lot of research is happening to understand this better. Of course, the heat is changing, so we add material, and basically the structure is cooling down, but still we need to wait at each iteration to cool down the joint. So we have to wait until it's cooled down before we print again. So a big topic is how to control this, and especially related to the amount of mass and the shape of this mass that is already deposited. A separate or very connected at the same time challenge is the modeling of the material, and this is quite challenging in terms of these varying conditions, and that is why in particular at this stage we go for an adaptive process where you don't know everything in advance, but you are measuring during the process to understand where you are to keep printing. But of course, to actually model the material, the behavior, and assure a good quality of the result, it will be needed to actually be able to model the differences on the position according to the torch orientations and how the material is according, for example, to gravity. So the main contributions of this work is basically to characterize the whole in-place adaptive detailing with WAAM, so the technique itself, and then propose a pipeline for integrating these fabrication constraints at the very start of the production process. And to end, I would like to bring a reflection. Maybe again connecting with the question from Roland, if we think what we will do with this, and it's just an image of a dome, that if we think abstractly, we have this regular pattern that it looks perfectly homogeneous and regular, but actually if we load it, we see that every single bar is different, and every connection or there are differences in the connection that actually have to be taken into account. So thinking in this respect, I'm looking forward to see basically using this method for solving these differences and acknowledging that in a structure, so where you can see actually the differentiation on the performance that is actually there, but by the way we build standardizing components or over customizing components, it's hard to see. So one interest is basically make this visible. So yeah, I think that's it. I'm very happy to take questions at the end of the session.
Thank you for this lecture. When I look at this and link it to Roland's question, maybe this technology, maybe this entire additive manufacturing, but especially your field, is the most applicable to all this biomimicry ideas and really following forces as they appear in designs as an activity. Philip is the one handling the question, and to give him an opportunity to is there any question, Philip, which we have to raise here now from the audience?
Yes, there's a question.
Perfect. Off you go.
First of all, very interesting way of applying the WAAM process in steel structures. I was wondering if you have previously investigated the mechanical properties of the point-by-point printed material, as it is widely known from literature that it largely differs from the traditionally manufactured one. In other words, how do you know that the printed adaptive node would sustain the design load?
Sorry, I need to switch my setup for a second. So you see me again?
Yeah, now we see you again.
Do you see me again? Cool. That it's going back and forth, I think. Yeah, so that's a super important point. So I'm not working here as a structural engineer of these joints. Sorry, I will just switch to this. That looks more fun. But we have done some tests to understand basically the performance of this material. So the first thing that we try, I'm gonna show a bit of that work in progress. 1 second. Yeah, so basically we are testing this material under tension loading to see how it performs and simulate the breaking points. So first of all, the big question is, okay, can we actually build with this material? Is this material strong enough to actually, it's a structural material? The result here is that it's quite similar to the original material, so S355. So it's actually, the result is quite good, but in a way that doesn't answer your question. Your question is the comparison between the continuous printing and the discrete. So here, basically we use the discrete because we could not use continuous print on air. So the idea is that we can actually use this technique to bridge parts that are not touching at all, which is basically allowing us to work with uncertainty and basically not super high precision setups. Is that your question, like the comparison between the continuous and discrete, or more like an actual AM metal technology prefabricated part?
I think it points to the question, but you also can then add on your discrete made line and continuous line to say then improve the next performance parameters. And I'm super happy to see the variety of these technologies, which we're going to see also later today, that there's so much research to be continued. So it feels like each field you dig in, obviously you do not exactly know everything, which is then again the open field for the next investigation. I need to stop here now. Thanks, Inés, for this presentation, and thanks for showing your mock-up last time on the beam in 2000 what was it, 18? No, 19. And hope to see more next time again in physical.